It's October 12th, 2020. It's more or less 11 a.m. Physics 174, page 1. All right, what's going on in life today? Well, let's talk about tomorrow first. Tuesday, hopefully you can see this now. Quiz number 9 is online and it should be due by 6 p.m. tomorrow. So it gives you a little something to do if you're sitting around bored to tears. Won't be bored, as somebody's saying, won't be bored. Wednesday, it's a student self-care day. So go take care of yourself. No class.
You get 1 day out of it.
You get 1 day.
I get 1 day off.
You get 1 day. I don't get any days, man. I'm sad. I'm the sad guy.
Who gives a day off on a Wednesday? Why not make it a long weekend?
Don't ask me that one. That's why I looked this up before this class to make sure I wasn't giving off erroneous errors because I kept knowing it. I thought it was a Wednesday, but yeah, I don't know. Why not a Monday? Why not?
Wednesday, not have Friday.
No, yeah, I can't do. Oh, if only you had my 8 a.m. class, we could have done that. But no, we can't. We're on a. I don't understand that at all. And there's 2 of them, I think, in the spring. So I don't know. Maybe they got their act together on that one. I don't know. Yeah, sorry. You're right. Probably doubtful. They're probably next spring is probably we're going to take a Tuesday afternoon off and Thursday morning. And don't. Oh, dang! I'm recorded on this thing. No, that's. Yeah.
Pick a weekend.
Pick a weekend. Thursday, homework number 8 is due by 6 p.m. I know. Oh, you think that's a boo? Here's Saturday's coming up too. Woo! I just threw them all on there.
Oh, what the hell?
What the heck?
Just give us the exam while you're out.
Throw that out there too. Yeah, class wants the exam right now. So,
And Sunday.
well, no, I gotta admit, I don't like to write because I'm used to the old days still. And I mean, I used to have homework assignments that would be 7 to 10 problems long, and they're really mean and they're ugly, and you're supposed to work on them for a whole week. And to throw 2 of them out there, but remember, it's only 2 problems each. It is bonus, so you don't have to do them at all. It's a very little amount of bonus. So don't think, oh no, I'm not doing them. I'm not going to get all this bonus. You're doing it. It's just as a little carrot to hopefully make you do a few of these problems. I mean, if you're going to stay for the exam, which when is that exam? Exam number 2 is on the calendar. It's going to be next week. Whew. But don't worry, it's as far as you can get away from and still be next week. It's going to be October 23rd, which unfortunately is a Friday. Yeah, you guys show up on a Friday. And well, no, you don't actually. Remember, it's online, so you just stay in your pajamas and get your laptop out and in bed, and curl up and do an exam. So there you go. So that's the goal on that one. So I'll give you more details about that when we get a little closer.
Oh, it's Mold Day.
Is it Mold Day? Yeah, you're right. It is Mold Day.
We can't have the exam. Yeah, it's a STEM field holiday.
That's is that national holiday, Mold Day? No, I'll look into that. Okay, I'll look into that. That's national holiday. So anyway, that's just it. But you might as well start getting ready for it. So you might as well try to do a few of these guides. There's 4 problems. Do 1 or 2, whatever you can do. And remember, it's just for a little bit of bonus. So it's not like the good old days where there were lots and lots of problems. You had to do them for a grade. So now the quiz, you should be actually the quiz is technically for a grade, but I think most people have gotten their 10 points. So I just kind of looked and rough estimate. I see a lot of 1s and I see a lot of 1.8s and 2s and all that stuff lighting up. So 4 or 5 of those, you got them. All right. So that's page 1. We're trying to get to page, what makes page 13? Oh, I heard that side. 13. But don't worry, some of them are very short pages. Just really 1 line and done. So can't wait for the short ones. Okay, so here's Page 2. Today we're going to talk about friction, and we'll have a little video, which you've already made. I've seen the video. It's just one, two. It's online, I believe. For those online folks who won't be able to hear good audio with it. But when I was in graduate school, I did my work at Argonne Lab outside Chicago, but my school was Vanderbilt in Nashville, Tennessee, and I got down there, and I'm from Illinois, and they'd get the threat of snow would cause them to cancel things. Seriously, they had a snowbird advisory, they call it. A little snowbird guy would come out on the news, and if they thought they were going to get snow, they'd close things. The schools would be closing, business would shut down, just on the threat of snow. And once, the first time we actually got some snow down there, it was like an inch of snow, and I thought it was fun. I was going to drive my car. It was a weekend. I was going to drive it out, get some groceries. I can drive in snow, no problem. That's when I found out why these guys really worry down there. They don't know how to drive in snow. They think if it's snowy and the speed limit says it's 45, they drive 45 miles per hour. They don't have to get farther away from people. And I learned very quickly, I did not want to drive in Nashville, Tennessee when it snowed because those guys were crazy. And we'll show a video of people in Seattle, Washington, even though it's farther north, think, well, they probably use snow. Actually, no, I guess they're not because they're near the Pacific, or right on the Pacific, and I think it gives them a very mild climate, and they're not used to snow up there, and you will see that in the video coming up. So be careful when you're driving, just because you can drive in the snow, and be careful when you're driving in the snow, but doesn't mean everybody else can too. All it takes is one idiot out there, and that video is going to be basically a video of idiots, people trying to do stuff in snow.
I don't know what he's talking about.
I don't know, but we know how to drive in snow. Not that I like to either. So that's coming up in another month or so. For physics 174, people are leaving my room already. How's that happening? It doesn't bode well on a Monday. I mean, we're only 12 minutes into it. Here's little ding dong people going out. Yeah, they're going to go out and play in the snow. For physics 174, the frictional force will exist only between two surfaces in contact. So no air resistance. There are problems in the back of the book where they'll start mentioning air resistance, but it actually gets very complicated. And we're just here to introduce it to make it more real world. So we're able to introduce an equation which is only an approximation for this force, but nonetheless it's a good one, and it gets us more in what's reality, what's really going on out there, so we can actually estimate some things. Of course, in life you go on in this area where you actually deal with frictional forces, airflow. I mean, let's face it, that's why they make the big wind tunnels. That's why they pay you the big bucks, hopefully, to overcome and study these phenomena more in depth and more exact. So, but our goal today is to get an equation. And it's only going to be a good approximation, but nonetheless, the key word is good. The bad word is approximation. That calculates the frictional force. So it comes to the frictional force. There's two types we're going to deal with. This pretty much encompasses all of them, but there are other ones. There's a rotational frictional force, which we're not going to talk about, but that's the other big guy that jumps in my head. But for us, we're going to be able to study it pretty well by understanding kinetic and static. If you're familiar with terms, and if you've had physics before, you may have heard the term kinetic energy. So that's the next chapter for us, part of the next chapter. Kinetic means motion, movement. So this is the frictional force we associate with movement. And then we have static, which everyone can static. If something's static, it's not moving at all. So it's either one of these two forces will be happening there. You don't have to worry about both of them interacting at the same time, which is great. So you never see both at the same time on the same objects. And I put that out there on because we're, you think, oh, I got to make a distinction between the two types of frictional forces. Yeah, I will initially. but we're going to find out, since they only occur different, it's one or the other, and their equations are going to look exactly the same, at least when we maximize out static. And because of that, I'll get in the very maybe a lackadaisic habit, but I understand because so many subscripts, oh, that's right, here's my frictional force is going to equal, here's this equation. And you say, well, I don't know if that's kinetic or static. It doesn't matter. It's the same form of it. You just got to remember when it comes to a certain constant I've got to put in there, that's where you got to worry, is that the kinetic constant I put in or the static. But once you know that, everything works out the same. Because little subscripts get a little messy in there. First guy up, kinetic. Also called sliding friction, or sliding friction force. And this occurs when one surface moves relative to another surface. Of course, that's in contact with. So you think about, a sled sliding across a snowy field, or if you've ever taken a dive in basketball or volleyball, going after that ball, and you slide across the floor, you're all too aware of sliding friction. It can leave a very, very nasty rug burn or floor burn on you. Of course, that also deals with the conservation of energy, but that's the process. We need some kind of symbol for it, or somehow indicate what we're dealing with, and we're going to denote this denoted by big F for force, little f for the frictional force, and at least to get us going here, comma K for kinetic. So there's your kinetic frictional force. Real exciting. And what we want to do is we want to get an equation. Need an equation for this. And I'm going to not necessarily derive it. I'm just going to actually, since it is an approximation, there is no derivation for an approximation, but I'll just give you, hopefully it'll kind of make sense here as far as where we get this formula from. If you don't like it, you just want to, it's Monday morning, just kind of close your eyes and glaze over there for a second. When I start boxing in something, that's when you want to wake back up and box in. Or since it's all videotaped and everything's going to be posted online, I guess you can just look for my boxes. Remember this statement. So, but to how to get this equation, or at least make sense of it. If all things but one are equal in the following cases, in which scenario would you have more friction, or would the frictional force be larger? It's a shortcut to say more friction. Really, we're saying the frictional force is larger in this case. So let's see. So we're going to be driving a bicycle up a hill. So let's draw one here. Have a little fun on a Monday. Little Sky Dog with a hat on him. There you go, buddy. He's having fun because he's on a bike. Yeah, let's see. Oh, I don't know what happened to your foot there, pal. Sorry. On a pedal. And I got some problems here with this bike. Sorry. There's your bike. All right, and over here he's on another hill or a more level surface. Let's see, go. There we go. Okay, a little bit better. Oh, sorry, you don't have eyes, buddy. There you go. You got some eyes now. Oh, no mouth. Kind of put a mouth on him there. There we go. All right. It's supposed to be a Scotty dog. My high school mascot was the Scotties. Until the school got demolished. Now it's no longer the Scotties. Now it's the South County Vipers. Oh, well. There you go. You guys going up the hill there. Not going up much of a hill here at all. He's in Illinois on this hill. Welcome to Pennsylvania there. So here we have a steep hill. And here we have a shallow hill or no hill. Well, where would your frictional force be greater at? So you're trying to pin up the hills. Which one would you have a greater frictional force?
The shallow.
Yeah, the shallow. Greater friction force. Here you're having trouble staying on the hill. I mean, you're starting to slide backwards. Matter of fact, if you get it too steep, you're on a cliff. And if you ever try to drive up a cliff, well, that's not so bad. You're just going to hit the wall. If you try to drive down the cliff, it's called falling. And you don't want to do that. So there's just no frictional force. Friction is actually good for us in several cases, including the ones I have already alluded to, driving in snowy conditions or slippery conditions. We want that frictional force there. When it comes to walking, we want a frictional force. You try to think, oh, I'd like to have no frictional force. If you try to walk with no friction, you're just sliding on ice. You're just literally going nowhere. So there's no there's a reduced frictional force over here. So what changes? Well, the angle changes, but how's that deal with forces? Does anybody know what forces change in between these two conditions?
The normal force.
Right, the normal force, right. That angle of inclination's got something to do with the normal force. Between the two cases, the normal force. Yeah. Try to put an E there for the. I mean, gravitational weight's the same, but the frictional force changes, and that's because your normal force is changing. The steeper the hill gets, the less Fn becomes, all things being equal, other than that, just the orientation angle, the inclination angle, and the less friction present. So from that great analogy with a mascot which no longer exists, we can say that the frictional kinetic force is proportional to the normal force. That's a fancy mathematical symbol. It's not really a Swedish fish or anything like that. One of those, little cheddar fishes, or what are those things called? My kids like them. Little cheesy. Thanks, goldfish. I hate those things. I hate those things. But
How?
it's
You like Cheez-Its?
no.
Whoa.
I know. There you go. I mean, it's all full. It's all making sense now, right? My opinion is wrong. I'm old. How can you not like it? It's great. It's my kids' snacks. I got snacks they don't like. You guys will get kids one day too, some of you, and you find out what snacks they don't like, so you can eat them all. And then one day their taste will change, and then you'll find out your snacks are all gone. So the big thing in my family, no one likes coconut except me. I know, but it's okay, because you'll find out that if you can tolerate it, you'll start liking it more and more, because it's always for me. Coconut ice cream, coconut candy, mine. Get your own.
For you, then.
Coconut cream pie,
That's a
mine.
thing? Coconut ice cream?
Yeah.
Ew.
What?
What's wrong with you? I can eat it, but my mom ate it. Oh, God.
They are doubting what coconut ice cream is. Alex, your mom likes coconut ice cream?
Yeah.
You don't like it? That's why. That's why your mom likes it. You know, you leave it alone. It's always in the freezer for your mom. Mine's always in the freezer. My cake I get for my birthday, coconut cake. You know, I know. At this age, I don't know if they do. They tolerate me, I think, but it's okay. It is. It's okay. I'm glad they put up on me. All right. So of course, we need an actual equation. The proportionality thing works fine. It tells us that if I double the normal force, my frictional force gets twice as great, but it doesn't give me an actual number. And we'd like to be able to do that. And to do this, we need, and we're going to play this game a lot in physics. Actually, you'll play it in second semester without me. I'll be traveling onward with the biology people, and they'll every day to them will be like coconut ice cream day for them. They'll just, not physics again, please. That's when they start taking bets. He's got to die of a heart attack sooner or later. He's getting old. All right.
You only have a heart attack if you have a bad heart.
Yeah. Yeah. The coconut keeps me fit, not the ice cream. We need to introduce a constant of proportionality. All right. So if you got a proportionality, the thing where, you know, the normal force is proportional to frictional force. If I introduce a constant in there, I can make this work. And to show you why this works, you've got an analogy to this. When it comes to area of a circle. The area of a circle is proportional to r squared. Right? So if I double r squared, not r, but r squared, then my area gets twice as large. Or if I make r squared 1/10 of the size it was, then my area goes down to 1/10 of the original value. We introduce a constant proportionality in here. Anybody know the constant we stick in here? Right, it's pi. Constant proportionality. And that makes it into a real equation. It's like Pinocchio, making it into a real boy. Constant proportionality. So then you no longer know that as r squared gets bigger, then a gets bigger along with it. Now you actually get a physical number. So if you know r is in meters, you can actually give me how many meters squared area the circle is. So we're going to do the same thing for that proportionality I just gave for the frictional force, the kinetic frictional force. Here comes the box. The frictional kinetic force is equal to, the proportionality constant is, looks like a U, but actually it's not. Does anybody know what this symbol is? It's a Greek letter. What do cows say on the farm? Mew, that's right.
Like the Pokemon.
I'm not familiar with that Pokemon. Pokemon character is called Mew?
Yeah.
I never heard that. I've seen Pokemon a little bit, but our cows on the farm are very smart. They always could speak in Greek letters, Mew. So there's actually a Pokemon character called Mew. Another person just left me. I didn't mean dang, I got to turn this little chimey thing off. I don't want to hear this. It's like the feet. Every time you hear a ding, ding. They've left you. All right, Greek letter mu. If you want to write it as U, that's fine, but your book's going to have it like a funky U. It's Greek letter mu. It looks like a U with a big, long tail. I don't know that you'd call that a tail, but a pre-tail. And we call this the coefficient of kinetic friction, because we got the coefficient of static friction coming up right on its tails. Now, I haven't finished my equation yet, so I guess I got to call this mu k. And then that's the normal force. So here we go, we're boxing it. There you go. So it's a very nice and compact equation, no derivatives, nothing like that, no squares, just find the normal force, take it times a constant, and poof, there's your frictional force. Now the little bit of a difference is, when I say constant, coefficient, I actually didn't say the word constant, good for me, but I said coefficient, you might think, oh, it's pi's 3.14, whatever it is, out to however you want, many decimals you like to remember them. It's a good party joke. If you think you can get people to leave your Zoom meeting fast, just start reciting the decimals of pi. This is a constant, but I put it in quotes. only when dealing with two surfaces of specific composition. Oops. Combustion. So if you're talking about the mu-k between, let's say, concrete and wood, you're sliding a wooden box across a concrete surface, that's got a mu associated with it, mu-k. If you replace the wooden box with a steel box, steel and concrete, different mu-k. So it's a constant for this. As long as the surfaces stay the same, you're fine. Now, I'll go one step further. Technically, it also depends upon temperature and humidity. That's overkill for us. I mean, obviously, that's your cup of tea. That's what your job is, to figure out that frictional force real exactly. And then you're going to need to know it. And if you've ever, where do I get some of these at, or where am I going to get these at? Actually, I'll just write them down, and then we'll talk about that. Oh, no, I'm out of paper. Don't think we're not out of the class yet. I got more over here. Don't worry. Don't worry. We cut down some more trees over the weekend. Please recycle whenever you can. So 6. To give you an example of this here, so here's one of these short pages for you guys. Surfaces and UK. So let's see. I made these up for the other class, but I actually went and got the book for you guys. Unwaxed hickory on dry snow. Anybody want to guess what UK is?
What is unwaxed hickory?
Hickory's wood, and you just don't wax it. No wax on it. Actually, does anybody know what maybe they're trying to describe? Unwaxed wooden. Yeah, maybe skis. I mean, skis are nowadays they're ones I've got are not made of wood, but yeah, skis.
Sled?
I don't know. Don't ask me where some of these guys. Does anybody know what anybody want to guess what UK is for that?
0.0.
Close. 0.08. Okay, we'll let you go. Let's see. How about brass on ice at -10 degrees Celsius?
0.08.
Oh my gosh, that's 0.075. That's you're thinking of that -15. That's what you're thinking of. Okay. You got natural rubber on vulcanized, on ground glass, on concrete, you got ebonite on ice. You think, where am I getting this from? I'm getting it from this book right here. It's a big book. It's got all kinds. It's probably got your guys' life story in or something. Probably got all our birthdays in or something like that. It's a book. It's called the. You might want to get one of these one day. You're an engineer. Heck, what am I saying? They're all online now. CRC. Does anybody know what CRC stands for? It's a great story in itself. This is the 62nd edition, way back in '82. I got this at a book fair for a book sale for a buck. My wife about died. Oh, she got mad when she saw me carrying this thing around. Yeah, and actually I bought a bunch of them. If you go to my office, this is the big guy. I got smaller ones too. Because the good thing about this CRC is, you want algorithms, you want all kinds of things, you want properties of rare earth metals, you want organic chemistry. There it is. And the thing I like about it is, where's it hiding at? Oh, there it is. Aha! Indefinite integrals. That's what I like about it. It's got indefinite integrals in it. Yeah, that comes in handy. CRC for a Monday morning. Anybody know what CRC stands for? It's a great example of how things sometimes go differently in your life than you plan. CRC stands for the Connecticut Rubber Company, if I still remember right. And they gave these out, if I can do the math right, around it looks like around 1920 was the first one. And it was very, very tiny at the time. And they did just like a advertisement. They were advertising. They made rubber, and they wanted to advertise their products. And as a just for so people wouldn't lose track of their advertisements or their they're trying to get the name of the product out there. They attached it to this little manual, which had about 10 pages at the time, which had things like not necessarily coefficient of friction, but properties, material, melting point, stuff like this. And people started asking them later on, hey, you know what? You wouldn't have to have a few copies of that nice manual with all the physical properties in it, would you? So they realized they had something that stuck in people's heads. So next year they came out with one that was a little bit bigger and a little bit bigger and a little bit bigger. And now we got this thing, which is, well, that was nice. They only number it's in sections now. So all I can tell you is that section F's got over 209 pages in it. So, so that's when they came out with the CRC handbook. It's gotten smaller, but it was well over 1,000 pages. Section F. There's a section I.
Sections and numbers.
Sections and numbers, and so so that's the and so people actually just wanted the and so they started this publishing this CRC handbook. They made money off that. I don't know exactly if the rubber company still exists. That's happens a lot like that in life and engineering. Does anybody know where tea bags came from? Oh. Yes, tea bag. I know what tea bag is. Oh God, you guys are just sad when you do that tea bag. It's like, come on.
Don't worry, it's not gonna make books.
Anyway, I've been tea bagged a bunch when my son's been like, oh, your dad, you try to play tea bag. Hey, tea bag me. Yes, it's funny. You got you're doing it to an old guy. Doesn't even know he's not a. The actual tea bags. You might know where the actual tea bag came from. Where they? China. Well, tea came from China. That's true, but no,
Scandinavia.
You were there was a tea sale. I forget who it was. You look it up in your time, but there was a guy going around selling tea. Wanted people to buy his tea. Well, he couldn't hand out whole cans of tea to the people. So what he did was he wanted to give a sample. He gave little samples out in little tea bags. And then when he came back around to see if anybody would buy it, he said, you know what, we like your tea, but we really want more of those little bags. It's really cool. Instead of me measured, they're already measured out. I can dunk it in my hot water and I can make tea out of it. And so the tea bag actually was invented by it was an advertising thing, just like the CRC handbook, and that became a whole industry. Okay, but blah, blah, blah. Back to reality. It's static friction now. I know, hang in there. I do the same thing. This is the frictional force between, I never guess this one's exciting, two objects in contact, but not moving. Yeah, put the big not in there. Not moving relative to each other. I get rid of this big book. It's hard to maneuver over. So let's see, let's draw a person here. Call this Yahoo. He's so he's sitting here and oh, sorry, I just broke your foot, buddy. There you go. This is a heavy mass. It's like a refrigerator loaded with Harrison Ford. All right, just for the nuclear explosion, that last horrific Indiana Jones. So this person is a supplying, we're just going to make it all horizontal. F of the person is a horizontal force by person applied to mass. By Newton's second law, we have a little bit of a problem. If you look at Fx, would mean the mass should move. But if you've ever pressed on a hard object or a big solid object, try to make it move, it doesn't move. You're applying a force to it. So what's stopping it from moving is there's got to be another force. Gravity. Well, gravity, yeah, it is there. But of course, it points downward. What other horizontal force is there acting on an object? Yeah, there's a friction. So they should move. It can't be. It's not moving unless there's a second force. Unless, let's just say, there's a counter acting force. And that's going to be the static friction force. Tired of writing today already. And that's going to be written as F, some F with a little S there. So it goes against the grain. Now, if I remove the person's force, so person just take a break, Bill. Bill stops pushing on the mass. Now there's a frictional force pointing to the left. Will the object start sliding to the left? In other words, when I stop pushing, no, the frictional force just seems like it magically disappears. And if the object is really heavy, like we've all been there, you try to push something and, oh, that's heavy, it's not moving. I'll push with a harder force, stronger force. I get FP gets bigger, and the object still won't move. So since Newton's second law is still going to hold tight, the frictional force is increasing with this person's force up until a point where finally the object will start to move. So, in words, well, written in words, as FP increases, the static frictional force increases as well, up to a maximum value. Eventually, you'll get to the point where the object will start moving, but when it starts to moving, now you no longer have static frictional force, you have kinetic. So this illustrates the matter that you only have static or you have kinetic friction. You can't have both at the same time. You can't be moving and not moving at the same time for these two objects. Up to a maximum value. At which point you have, let's just say you have kinetic frictional force. Kinetic friction as object is now moving. So for the equation for the static frictional force, it's going to look a little weird here for a little bit, not for one line or two. For the kinetic friction force, it was mu times Fm, we were done with it. But the frictional force for the static case starts at 0 and it goes up to a certain maximum value. So it's actually written by inequality as an inequality is the frictional static force is less than or equal to, we're going to need a coefficient of friction or a coefficient of proportionality, which is going to be mu again, but now it's mu s times Fn. Let's see. Coefficient of static friction. So this is a nice equation to know, at least for a while. But when we numerically want an answer, at the point of motion, the static frictional force equals a maximum value, which by this equation, this inequality equals this mu s times Fn equals max value for static friction. So you'll see a lot of problems written like that. At the point the object is about to start moving, at the point the object will start or begin motion, or then you know you can apply this equation. We never deal with this other than just on exam. Maybe I can ask you a conceptual question about it, but as far as numerically goes, it only allows us to get an upper limit to the frictional force. We're more interested in actually knowing exactly what it is, and that only happens at the moment you're about ready to start the object to move. So this guy here is useful for actual numeric calculations. It's what your problems are going to be based on. So, in other words, if the inequality is scaring you, don't worry about it when it comes to doing the math ones, okay? We definitely know one thing, we're just about already, it's the equation for kinetic and static friction force look exactly the same except what coefficient you stick here. So if you're lucky, there'll only be one mu given and you just go with it. You don't have to worry, is that kinetic or is it static? It's only mu given. The formula will always look the same, mu times Fn. If there's two mu's given, you got to sit there and look at it. Now, is that going to be mu s or mu k? And you got to make the call, is the object actually, are the two surfaces moving relative to each other or not? And that's kind of a hard problem at times. If you're walking, you think, well, I'm moving. That's obviously kinetic friction. No, it's actually static friction because you want your foot to do what relative to that ground? You want it not to move at all. If it does move, what are you doing? If your foot moves relative to the ground, what's that better known as?
Ice skating.
Ice skating, yeah, ice skating, sliding, or a worse terminology for that for people my age, slipping. You don't want to slip. So you might think, oh, you know, so when I'm moving, my foot is moving relative to the ground, only when you're slipping. And we generally don't want that to happen. So actually, sometimes you got to look at it really hard. Bicycles the same way. You want your bicycle to grab the road. You want your tires of your car to grab the road. So the contact point, I know the tire looks like it's moving, but the contact point, you want it to be stationary relative to the ground. Then the wheel rotates and a new point's on the ground. You don't want to slide. That would be true kinetic friction. And you know what happens when that happens? You usually fall down. So generally for two surfaces, but US and UK, which one's bigger generally, US or UK? Close. US. Now the other class asks, when is that not the case? And I got to look through my CRC and try to find it. But generally, US is bigger than UK. And that's, just think about what happens if you got that large object, that refrigerator, and it happens to us all. I can still hear my dad shine, my brother shine, my wife, my kids all shine. You get the big object moving, and they'll say, oh my gosh, whatever you do, don't what? Stop. Don't let it stop. And that's because of this frictional force. The static frictional force generally is much larger than the kinetic energy, or the kinetic frictional force. The frictional force when it comes to static is always, almost always, larger than the kinetic frictional force, which is why when you get something moving, you don't let it stop. So just to illustrate that. Surfaces, wood on wood, US and UK. So 0.4, and from UK it's 0.2. So it's going to take, the frictional force gets half as large when you get it moving. Now these aren't proportional though. This throw one out here. Of course, this depends on what temperature the ice is and what type of ice. But here's the ice is 0.1, but when you go to UK, it's not half the value. It's actually, you know, this value here is only 30% that value. So yeah, boo. So generally, but in most cases, it's helpful when it gets moving, you don't let it stop. All right, the last thing of this, and then we'll do a little video. Yay, like that. And then we come back and do a problem. General stuff about mu and friction. Okay. A, mu is unitless. I'll just use, and if I'm gonna put S or K, this is just in general for either one of these guys. You know, if you want to see it though, the frictional force, once again, write real generically, is mu times Fn. You know, so this guy's in newtons, frictional force, and normal force is also newtons. Well, what do you multiply? You can multiply a number by the normal force and still get newtons, but you can't multiply, mu can't have any units of its own. So it's unitless, which is great. You don't have to worry about conversions or anything. It's just it's like literally it's like pi. It's a number and that's it. Mu is never negative. If it's negative, you've done a math mistake, or I've done something, a problem, which I'm always worried about that, including the ones that are out there right now, that I haven't checked it that one last time. I check it several times, but you know, you're used to the problem, you make the same mistake twice or 3 times. So it should never be negative. If it's negative, then if it's in the back of the book, then most likely just look back at your math. You probably got a negative sign out of whack there. Generally, mu follows a very specific range. Generally, mu goes between 0 for either static or kinetic up to about 1. It can be higher than 1, but just barely, and only in specific cases. I'd be worried about it if it comes up higher than 1, and especially if you come up to mu of like 10 or 100. That's beyond it. You go back and check your math again. Rarely higher than 1. So you should be expecting values which are positive between 0, some fractional number between 0 and 1. D, the frictional equations, you know, generically just written like that generically, are magnitudes only. Even though they were forces, I never had an arrow above any one of them. And that's because, you know, how do I get direction? Well, they're still forces, so you got to assign the direction. You assign the correct direction, U, of the friction force. Such that it opposes motion. So if somebody's tugging a wagon to the right, on your force diagram, you draw the frictional force going to the left. This would be for the kinetic case. Or in the case of static, the direction the net force is attempting to move object. This is your static. So go back to that large heavy mass that had the little cartoon figure trying to push. The guy was trying to push to the right. The static frictional force has got to pull to the left or be directed to the left. Okay, so when it comes to these force diagrams, I mean, the only thing we've done is we're just doing chapter 5. We're in chapter 6 technically now, but the only thing we're doing is we just introduced this frictional force. So we're just going to do force diagrams. Now you can have a frictional force, and this is an extra arrow you got to stick in there. It's an extra arrow. You got to make sure you have the point in the right direction. Obviously, it won't work out. Right? So that's that. Let's see a little video of this where friction's your buddy. Oops, somebody's got a biochem meeting. I'm sorry I didn't catch it right now. That's they're already gone. So somebody already left me for a biochem. Why would they leave me for a biochem meeting? I can think of a lot better reasons to leave. Like I'm just tired. All right, so let's share the screen. So let's first of all, let's get this thing back. Okay. Now I share the screen. Okay. Share the screen with those guys. All right, so you guys. So if you want the sound will come up better if you're online, if you actually look at the video. Or you sit there and watch the picture of the people. Not being too smart. Come on, baby. Here we go. Okay, so here we go. And of course, as I make all my videos, I gotta set up the music. Music is sung by Ray Bolger. Anybody know who Ray Bolger is?
He's the guy who sings the music.
Yeah. He plays the Scarecrow in Scarecrow.
Oh, the Wizard of Oz.
Was it right? And what the song does he sing? No. If I only had a brain. All right, here we go.
Don't laugh at me. I caught this on tape.
I could while away the hours, confer with the flowers, consult and with the rain. In my head I'd be scratching while my thoughts were busy hatching if I only had a brain. I'd unravel every riddle for any individual in trouble or in pain.
With the thoughts you'd be thinking you could be another Lincoln if you only had a brain.
Oh, I tell you why, the ocean's near the shore. I could think of things I never thought before, and then I'd sit and think some more. I would not be just a nuffin', my head all full of stuffin', my heart all full of pain. I would dance and be merry, life would be a ding-a-dairy if I only had a brain. Gosh, it would be awful pleasing to reason out the reason for things I can't explain. Then perhaps I'll deserve you and be even worthy of you if I only had a brain.
Oh no!
I feel sorry for the guy who actually just sailed out of the water, so I didn't look like he was doing anything too fast. Went crazy. Just some dad just gone. The guys on the inner tube who overshot the water, I mean, it looked like he was doing nothing funny. He was having fun with his friends, and they just didn't make the stopping area large enough for him. But the other people, though, they kind of seriously skied off a cliff. Whew, man.
Like, that's a
Well, the ones I found were the ones who lived. I mean, there's probably all kinds of ones out there if you want to see the guys who don't make it. But
what about those cars? That one car struck the other.
yeah, it has no
Does it have
friction.
to the brake part of the car?
You just you once you see them piling up down, you think I'm not going to try this, but no, I can make it. There's always a guy I can do this. No one else is, but I'll show you how to do it. Oh, let's see, where's that overhead at? Handout. Let's see, I got a handout now. We're going to look at the handout to do one of the problems, and then we'll move on. We're looking at this overhead here, this worksheet, which I got to hand out to the guys in the class. And I've got the stick figures already drawn in there. So we're just going to do the first one. It's an age-old question: should you push the cart or should you pull it? Which is better, of course.
Either, just don't move.
Right, don't move at all. That's my. Let me get a kid. Hey. That's why you got kids, right? You guys may not have. I got them. No kids. Well, I'm getting to the point where they can mouth me back. Now I'm not going to think about them right now. No, I'm just trying to think about it. Move that sponge around. There you go. No problem. You're welcome. So of course, it's the punchline's been ruined here because the answers were given, but the quandary was whether or not you should pull or push a cart, all things being equal. Of course, the carts are designed differently, so they're meant to be easier to be handled one way versus the other. But you see somebody in an airport, if you could design a cart, where you could push or pull, which would be the best thing to do as far as overcoming friction? So we're going to do this problem twice. We're only going to do it once. We only have time for it once. You guys are all sad. Or we'll actually compute the acceleration for the pushing aspect of it. So everything's constant in every scenario. They're same surfaces, same mass, same person, same force magnitude. The only thing that changes is the orientation angle of the person applying the force. In the first one, they're pushing it, which has the effect of the force being directed down into the ground, which is what would happen if you're trying to push a shopping cart in the grocery store, versus trying to pull something like perhaps a cart or a piece of luggage or something like that, so it's got wheels on it. So we'd like to figure out AX. That's our big goal right now. So can we find AX? Of course, we know what the answer is. It's right there. Let's see if we can find it. For the pushing case, let's draw a really big force diagram so I can draw all kinds of arrows everywhere and get the angle. So there's our mass. It's whatever the 40 kilogram mass is on wheels or luggage or whatever. And the only thing given to you, the first thing I do is slap down that positive X, positive Y axis. The only thing given to you is this force. F equals 100 newtons, and this angle is 30 degrees. Let's see. Now, how do you know there's actually, that's a good question, I didn't address it. How do you know there's a frictional force in here? Up until this point, we never had frictional force, and suddenly I'm talking, oh, it's a frictional force. How do you know there is a frictional force in this problem? What's the tip-off?
It gives the UK.
It gives the mu k, right? It gives that mu k, it gives you a coefficient of friction. So if you're looking at a problem that is there friction here or not, either A, you're solving for the mu, you got to determine if there's a frictional force. It's actually one of your homework problems, or they give you the mu. And when they give you mu, you should be thinking friction's here. So they say mu equals 0.1, I believe. And they also say technically it's mu k. And we know the mass to be 40 kilograms, and that's it. Okay, so you have to draw your force table. Name me a force that acts on our mass. Quick, name the good one.
Friction.
Okay, that's wasn't going with that one. The easiest one I was going to go with, well, was weight, but the frictional force, we could do that. The person is trying to move the cart to the right. That's the direction of this guy's force. It's off at an angle, but his x component is nonetheless to the right. So the frictional force is going to be going this way. Okay. It's on a surface, so there is a normal force. There better be a normal force because there's a frictional force. Can't have, for us, we can't have a frictional force without a normal force, and that's going to happen anytime we're in contact with a surface. I mean, air resistance is a different story, but we're not going to talk about that. And the object has weight, Fg, which I quickly just bail that out, right, mg. I mean, unless it's given to me, I'm going to automatically be taking the mass times g, and that's going to be g just 9.8, not negative 9.8. We're going to be using Newton's second law, so we've got to get a bunch of angles here. Now, you work with some of these, long enough, and most of you already have reached that point. Some of these think, yeah, it's a 9-degree angle. I don't have to worry about that made for the x component or the y component. But if you're a little new to the game still, I'll draw it all out. We always measure angles, if possible, from the positive x counterclockwise, unless it's convenient to do so, not to do so. But then you got to be very careful about cosine theta and sine theta, whether it's going to be the right positive or negative signs, specifically the right negative sign. Frictional force always opposed to motion. We're trying to move this thing to the right. And when it comes to a cart or a suitcase, you're not trying to lift it up off the ground. So this guy's going to be going in the negative x direction. In other words, F equals 180 degrees. Your weight hangs down at a 270-degree angle. And you can work with this 30-degree angle if you like. Or the big proper angle is 330. So whatever you like to work with. You can work with the little guy or the big guy. The big F is in the fourth quadrant. So I would expect its y component to be negative, its x component to be positive. So if I work with the x component, cosine 30 and cosine 330 are exactly the same thing. Sine 30 and sine 330 are magnitude-wise the same, but this would they'd be off by a negative sign. So I got to be very careful if you use 30 here. I got to stick in a negative sign for the y component, not for the x. I know. Let's go back and watch the movie again. Sounds like better stuff. We're going to get a number here. We're going to call it a day. So once you do your force diagram, you want the acceleration, run the Newton's second law. The case is being pulled along the floor. So in this case, let's say mass pulled along floor. So AX doesn't equal 0, but AY does equal 0. So if you've got something confined to a certain axis, that's great. One acceleration is 0 and the other guy is not. So this guy's actually a static case. And this guy's a kinetic case. That doesn't matter. I mean, it's just this guy's moving. Like I said, if you're used to the fact that you think, that normal force points straight up, the weight points straight down, they're not going to have any x component. That's fine. You don't have to write what I'm about ready to write. But for those guys, like I said, it's a little bit new to them. I'll do what I did in the old days. If I sum up my x components, I got to write every force up here and write their x component. So it's the normal force is x, the weight's x component, frictional force is x component, and finally Fx from the actual person themselves. M times A, mass is 40, and AX we're trying to find. But way back to chapter 2, what did I do immediately after this? And this isn't going to tell me anything. I've got to break my vector into components, so I take my normal force magnitude, I take it times, if I measure those angles relative to the positive x, cosine theta n. Same way for the other guys. Fg is just m times g. You'd have to do it eventually anyway. Do it right now. Cosine theta g plus the frictional force. Well, frictional force is going to be our uk times Fn cosine theta f plus f times cosine call it theta k. Actually, I'm glad I got the little k there because it may be easier to see versus my two f's are going out. I got a little f and a big F, but one f's got the little k with it. So you plug in as many values as you got now. Normal force, cosine 90 degrees. I didn't put in my m and my g, but bear with me on that. See what's going to happen here. 270 degrees plus 0.1 times Fn cosine 180 plus 100 times cosine. I'll go with a big angle. It doesn't matter for the x case because cosine 30 and cosine 330 are the same. It's in the fourth quadrant. And then you have fun if you got 90s and 270s and 180s. Plug in your calculator anytime. I mean, save yourself some time here. Cosine 90, you see something like that, plug in your calculator, it's going to be 0. 270 the same way. Cosine 180 is not quite as good as being a 0, which is fine. It's going to be a -1. So when the dust settles on this, we're left with -0.1 Fn, normal force, plus 100, cosine 330, equals 48x, or AX equals -0.1 Fn plus 100 cosine 330, all those are 40. Drat, I don't know Fn. And we've only been messing around with the x components and what happens in projectile motion. If we know something, we want something in the x, and boy, we're getting, we don't, there's an unknown we don't have what we need, like let's say time. We know what we do, we shift to the y's, and maybe the y information is going to give me the time, then I can run back to my x and I can find what I need. The same way here, if you find something lacking for your x components or the y components, you look to the other force components. All right, so in other words, and it should kind of make sense. Fn, we know it, we've already eliminated him, he's all y. And the only reason he's still standing is because of that frictional force. So let's go in the y components of our Newton's second law, and let's get Fn. Oh, I said 13 pages. This one's going to go 14. That's going to look too big somewhere. So the force in the y direction is equals MAY. For this case, we've already determined he's not moving in the y direction. You're pushing along the ground. You're not lifting it up. You've gone to all this trouble to write this long equation out. So for the sum of the force in the y direction, it's going to look exactly like this. Angles, magnitudes, except we'll have sines versus cosines. So I'm just going to go back and now let me write one extra line. How about that? So, folks are a little new. So I want to write my y components for all my forces. Somebody's laughing outside us. 0, of course, AY is different than AX. And then I mimic this equation right here, except I write sines in place of cosines. I should have wrote the m's in now. All right, well, I didn't. Okay. Now you got to be careful here. If you use the 30-degree angle, that's negative, so you need to put a negative sign here if you write sine 30. Sine 330 will give you the negative number. So if you write sine 330, don't put the negative sign in there. Sine of 90 is just 1, so we get Fn plus 40 times 9.8. Remember, this is the magnitude of a vector, so I know a lot of us still want to put a negative 9 point in there. That's not what you can do now. The sign will be taken care of by your angle, your sine or cosine, whatever the angle you got there. The g is just 9.8 now for the magnitude. Sine of 270 is a -1. What am I doing this for? Dang it, too late. Sine of 180 is 0, so that whole thing is going to go away. It's 100 sine 330. 0. We only have one unknown. This guy's gone. And when you solve for Fn, it is 40 times 9.8 plus 100 times 30 sine. That's what I wanted to get my answer. Plug in the A. Back here. Plug this value up there for that guy. Cosine 330. All this over 40. And AX is 1.06, which is the answer I've got. So that must be good, right? So we can't go back and redo the problem in the time given. We've only got a couple minutes, so you guys are actually getting out early compared to all the other classes. Good for you guys. What differs is if you go back and do the second case, what changes is, well, the x components are all the same. Cosine 30 and cosine 330 are the same value, so this equation is all going to look the same for you. The question of what differs is it's a normal force, and when you're pulling it, this is definitely a sine of 30 degrees at that point, and that's a positive number. So your normal force actually decreases when you're pulling something. You're lifting up on the object, so the normal force is going down. And because your normal force goes down, your frictional force goes down. Now the bell should be clicking. The bell should be going off now, and things should be clicking. Your frictional force goes down, and you're applying with the same force. You're going to be able to accelerate at a faster speed. So your acceleration would be greater for the pulling case. So if you want to, all things being equal, you'd like to pull something versus push it. Which in a supermarket, why do they put the cart in the front then? If it's easier to pull it, why do they have the cart in the front? You ever seen a bunch of people run through the supermarket with carts loaded with food and stuff like that? It would be fun to watch, but that's not safe. So you're not supposed to be going through the supermarket as fast as you can. You don't need to accelerate. You're supposed to be nicely pushing. Also, they want you to push nicely so you can buy lots of their food from them. You don't want to go through too fast. You won't buy stuff from them. So, but for
behind you, you're gonna smack the wheels off it.
there you go. There's all kinds of reasons for it. But yeah, so it's in the supermarket. You're not trying to do things fast. You're trying to be able to control it easier with minimum safety hazards to old people like me. So there you go.
If you put it like that, then I'm gonna be reckless.
There you go. You can try to break the Olympic record for supermarket cash or stash or whatever you want to. I bet you there's got to be something online where the people do that as fast as they can. Why not? It's ESPN3 or whatever. Red Bull shopping spree or something like that. Right? All right. That's it, guys. So I got office hours today. I'm gonna get some lunch. I'll be back and zooming after that. You guys take care. Have a good health care day. I'll see you guys on Friday otherwise, all right?